Let's take a look at the LLVM source code. Yesterday, I looked a little bit at GCC, and that was exciting and fun. I thought I would take a look at LLVM to get a sense of how they are different, and I think that will inform my understanding of what GCC is up to as well. So as with the GCC case, again, I haven't looked at this code before. I don't even know if I've ever used LLVM or Clang directly. And so I'm going into this mostly blind. So I'm just going to poke around, try to get a sense of what the different directories are doing, and just build my familiarity with the code base. Okay, so I'm looking at their GitHub repo. I see that they have a separate place for submitting patches, which is a Fabricator installation. I guess I might poke around here in a bit, but why don't I look at the source code first? Okay, so in here we have, so Clang is part of the LLVM project. Okay, I was not entirely sure that was the case, but it's in the same repo. Let's see. Compiler RT, Flang libc, LLD, I assume is the linker. Although, is this an LLVM specific linker? Okay. LLD is the source code for the LLVM linker, a modular class platform. So what is the GNU linker? Is that just LD? I think that's just LD. The GNU linker. Okay. Cool. So this one has two L's. I assume the first one is for LLVM. Okay, so we'll look in the LLVM directory. There's an LLVM libgcc directory. What is LLDB? I don't know. All right. Okay, so you're not going to tell me what's going on in this directory? GCC sver. There's not much going on in the LLVM libgcc. Here's a doc. Enabling libunwind as a replacement for libgcc on Linux has proven to be challenging since libgcc._s.so is a required dependency in the Linux standard base. Some software is transitively dependent on libgcc because glibc makes hard-coded calls to functions in libgcc. Okay. So I guess this is building libgcc with LLVM. I will guess that's the case. Okay, so let's take a look at this LLVM directory. Examples. Yeah, sure. Let's look at examples. Lib projects. What is projects? Let's take a look at what projects is. Resources, runtimes, test, tools, unit tests, and utils. Okay, so this is a much, this seems to be a bit more organized than the GCC code base. Okay, contains source code for LLVM, a toolkit for the construction of highly optimized compilers, optimizers, and runtime environments. I'm guessing maybe lib is the place to be. I don't know. Utils. I guess let's look at utils, and then just out of curiosity, what is .in? This is some sort of metadata description of the project. I'm not sure what it's for. Okay, how to use JIT, how to use LLJIT, IR transforms. So this is the examples directory. JIT I assume is going to be just-in-time compilation. Here's a demo. Brain F. Okay. Is this a full parser? Fibonacci. All right, so what is this Fibonacci? This small program provides an example of how to build quickly a small module with function Fibonacci and execute it with the JIT. So I wonder how much of LLVM is about just-in-time compilation. Because this is what? This is a C++ file. Initialize native target ASM printer. So I assume this is going to print the, ASM. Assembly? Then we need an LLVM context. So create some module to put our function into it. We've got owner, new module, test, context. Create fib function. Okay, so what is create fib function going to do? It's going to return a function. Now, is function an LLVM thing? I think it is. Okay, so LLVM/IR /function.h. Okay, so it's going to create the fib function and insert it into module M. This function is said to return an int and take an int parameter. Okay, so where does that happen? So function type get int 32y ty. I don't know what the ty is. Okay, so this is going to be the fib function, and I guess that this is setting up the maybe the return value and the arguments. So it's taking a something in curly braces. So some kind of container, I assume. Okay, and so we have fib. Oh, type is ty type. Okay, so we have the fib type. I see, and then we're going to create the function by calling function create with the type. This is just a way, I guess, of encapsulating the type information as a single argument, and function external linkage, I guess, is some setting that says to do external linkage. Fib is maybe its name, and M is the module that it's in. Add a basic block to the function. All right, so we're going to do basic block create on the context. We're going to, I assume, call it entry block, and it's going to be in the function fibf. Get pointers to the constants. To which constants? Okay, so that we're going to get value 1 and 2. Okay, so these are the, I guess, the numerical contents, numerical constants 1 and 2. They're building up. I assume we're going to build it up recursively. Get pointer to the integer argument of the add one function. Argx. Get pointer to the integer argument of the add one function. So this is going to be an argument, which I'm going to guess is also an LLVM type thing. It's going to be called argx, and it's at argbegin in fibf. We're going to set its name to anarg. Give it a nice symbolic name for fun. That is fun. Thank you. So we're going to create the true block and create the exit block. So we've got return and recurse. So I don't know what the name of a basic block is. Is it just for human consumption? I don't know if it shows up in the code anywhere. But this is going to be return, I guess, is obviously going to return, but that's like the base. That's going to be the base case. And then we have the recursive case. Create the if arg less than or equal to 2, go to exit BB. So I comp inst, I assume is comparison inst. I don't know what inst, maybe comparison instance. And this is maybe a conditional instance. We're going to pass in BB. Where is BB? BB was the basic block. Create a basic block. Is this like the outermost block? And ICMP SLE. argx2, and I guess we're calling it condition. I don't know what. I compare instance. Oh yeah, okay. So we're just I compare SLE. Just out of curiosity, I want to know what this is. Can I click on this? I compare SLE. Where is this? This is in Doxygen. I just kind of want to know what SLE stands for. Signed, okay. Signed, less or equal. All right. So we're going to do less than or equal. And branch instant create return branch, recurse branch. I see. So I guess this branch, we're creating a branch, and the stuff that we need to create the branch is we need the condition that we just created that's going to tell us what, logically, when do we branch. We need the basic block, which I'm guessing is kind of just like a root node to a tree, kind of like a tree that we're building. We need a recurse BB, which was the recursive case, and then we need the return case. So, all right, that all makes sense, I think, assuming that I'm understanding this correctly. And we're going to create ret int1 return instance. I assume create context 1 ret BB. Now, what was 1? 1 was the constant one. Okay. And then we're going to recursively call, and we have a binary operator create sub. argx1 arg recurse BB. What is sub? Is it like a sub function? And we're going to call inst create a fibf sub fibx1 recurse BB call fib, and then we're going to do set tail call. Okay. Yeah, right. So we're going to do a tail call, and I guess this is kind of like a sub function. I'm going to look up. I can't click on these in GitHub, but I can search the internet. Create sub. Not sure if that create sub whatever is what I'm looking for. Oh wait, let me fix this video glitch. Let's try this. Okay. No folder create sub. I don't know. All right, I'm not sure what create sub is, but I assume it's kind of like a sub function. All right, and then we've got this other fx minus 2, which is more or less the same thing. And then we're going to call their sum create add. We're going to call, we have a call from fib1, fibx1, a call from fibx2. I think we're just going to name it add result. And we're going to, what is recurse BB doing here again? I'm not sure. Is that where maybe that's where the control returns? And we're going to call it sub. Okay, so we've created, I see. So that's actually relatively intuitive, what it's up to. And so it's going to initialize native target, ASM printer. You've got a new module, which is just going to be called test. And what is owner? Maybe it's a module owner. We're about to create the fib function. So we call create fib function, which returns this function. And now we're creating a just JIT. We've got an error string execution engine using the builder. Set error string and create. We're going to move the owner. We're going to move the owner object. It's going to be owned by the engine builder. And then we check the error condition. So is this error string? Wait, what is E? Yeah. Oh, if not EE. Okay. So we're not checking the error condition. We're checking whether we got a, I guess a null pointer back or not from as the engine. And then errors. Or we're going to just print out some stuff. We're going to verify the module. If verify module, error constructing function. Wait, so does verify module return true if there's an error? If verify module, okay. Then we're going to we'll print out some more stuff. Call the Fibonacci function with argument n. So we're going to create a vector with args1, args0 in value is equal to API int 32n, generic value, EE run function. So generic value, I guess, is kind of like an any type. And well, let's see, where do we pass in args? Sorry, we get, okay. Sorry, we're just creating the vector here. And then we're assigning its 0th position to this particular integer. So that's args. All right, so this run function, I guess, must take in a vector of generic values, which are the arguments, and it returns a generic value, which is the return type. And then that's it. Okay, that was actually pretty informative. I'm a little bit surprised at what's going on with verify module. Maybe I'm misreading this code, but kind of looks like it returns true if there's an error. So let's look at verify module. Did I not type it correctly? Verify module. Is it defined here? No results in code. Okay, we got check a module for errors. Hey now. Did I click on the wrong thing? I'm looking at verifier 8 .h. So maybe I can look up verifier. What? Is it in utils? What have I done wrong here? Verifier.h, file reference. Can I see the source code? Classes, namespaces, functions. Include dependency graph for verifier.h. This is just where I was before. Source file. Okay. Verify module. Check a module for errors. If there are no errors, their function returns false. Okay. If an error is found, a message describing the error is written to OS if non-null, and true is returned. That seems a little bit backwards. I'm sure that that's a source of common bugs as you're writing a LLVM plugin thingy. Kill the doctor. Yeah, let's check this out. What is kill the doctor? This is a util. Kill it. Prevent Dr. Watson from stopping tests. It provides an extremely hacky way to stop Dr. Watson from starting due to unhandled exceptions in child processes. So what is Dr. Watson? This must be like there's. Why am I finding no code? No, couldn't find any code matching Watson in the LLVM project. But Watson is right here. What's going on, GitHub search? Okay. Oops. Oh, hey. This is a tiny font. Diggs BTW7. I don't know what's up. I know it's Valentine's Day, so that's exciting. I don't know what Watson is, but I'm going to guess it's some sort of test runner. The Dr. Watson program. Oh wait, is Dr. Watson a Windows thing? It's a debugger. Yeah, we know it's named for Sherlock Holmes. All right, it's a debugger included in the Microsoft Windows operating system. Not to be confused with Sherlock. All right, great. So this is just going to kill Dr. Watson. Okay, cool. So that basically told me a lot of what I wanted to know, which was what's going on with kind of how LLVM does things. And so I guess if I'm going to summarize what I think I understand from that example is we have this C++ syntax for building up a generic representation of functions, and it's pretty intuitive and pretty straightforward. I don't know what that gets compiled into. I'm guessing that it's going to be some kind of tree. Let's see if we can find out where that is. So we have binary format ASM parser, bitstream, code gen. I'm going to guess happens after the tree is built up, but maybe we can take a look at that. Demangle. Oh, is it execution engine? Oh, no, it's IR. That's what I want, right? Yeah, I think so. Option, passes. Let's take a look at passes. Remarks. This is a way of, maybe that's a way of annotating the tree. Target testing, tool drivers, transforms. And yeah, let's look at X-ray. Did I already open this? Okay, let's get out of here. What did I open back here? Anything interesting? Utils. Perfect shuffle. Visualizers, reviewing. Table gen, cross tool, count. Emacs. I wonder if these are, I'm kind of curious what they're doing with Fabricator. I wonder if like Emacs and, so there's a bunch of code editing software that I recognize, like JEdit, Kate. Lint is not code editing software, but I'll look at the lint directory. I think I saw Vim somewhere. So I'm guessing these are like LLVM supports for these editors. Indirect calls, LLVM compilers, check. Reduce pipeline. All right. Let's back. Let's get rid of some of these tabs. Okay, so we're in perfect shuffle. Generate neon. So a mask is a 4-nibble hex number. Okay. But what are we masking? We can make a mask. Oh, is this just, wait, let's see, perfect shuffle. So let's see. We can call make mask, and it's just going to do the bit wrangling for us, I guess. 1 times 4, 0 times 4. We can get a mask element. So this is just a nicer interface, I guess, to doing the bit. Is it called bit twiddling, or is that something different? If we're doing all this stuff by hand. Get compressed mask. Turn a 16-bit uncompressed mask where each element uses 4 bits into a compressed 13-bit mask where each element is multiplied by 9. Okay, so we've got a 16-bit uncompressed mask, each one using 4 bits, and we're going to turn it into a 13-bit mask where each element is multiplied by 9. But why? For why are we multiplying by 9? I don't know. I'll have to work that out some other time. Okay, here's a shuffle operator. This represents a shuffle vector operation. Cost. I'm not sure. I also don't know what neon is, but all right. So see the table with accessors. So I'm not really sure what's going on here. We're doing some sort of shuffling with masks, or I'm assuming we're shuffling like bits around to do something mildly fancy. But what exactly that's doing, I'm not quite sure. All right, Emacs. These are the syntax highlighting files for Emacs and X Emacs editors, and they're apparently in Lisp, as you would expect, LLVM mode. All right, cool. It's like a giant, bunch of giant tables. All right, so special instructions, fi tail call. So these are, this is basically like a big list of regexes for, oh, okay. Is this how things work in Emacs? We get a regex, and then that regex is used to match different types like keywords or operators. Okay, cool. Ooh, fabricator. Okay, this is some sort of fabricator patch, maybe? Is it a patch to fabricator? I guess so, because it's in PHP, right? Okay. Lint. Are these... I'm not sure if these are linters for the LLVM codebase or if this is tools for implementing a linter based on LLVM. Generic code lint. Max length is 80. Checks files to make sure they conform. Okay, conform to the LLVM standards, which can be applied to any programming language. Okay, so this is linters for LLVM. So I'm going to ignore that. Wait, what did I just do? Reduce pipeline. All right. What is YAPF? I don't think I know YAPF. Google YAPF. Okay. It's based off client format, and it takes the code and reformats it to the best formatting that conforms to the style guide, even if the original code didn't violate the style guide. The idea is also similar to the Go format tool for the Go programming language. End all holy wars about formatting. Okay, so it's some formatter. So this is Python, right? All right, so verify. Okay, but what pipeline is this? Script for automatic opt pipeline reduction for when using the new pass manager NPM based around the print pipeline passes. The reduction algorithm consists of several passes. First, verify that the input fails with the given pipeline. Make note of the error code. Split pipeline into two, starting from front and move forward as long as the first pipeline exits normally and the second pipeline fails with the expected error code. Okay. And remove passes from the end of the pipeline as long as the pipeline fails. But what is this pipeline? I don't know, but it's in Python, so I don't think this is... It seems like some kind of utility. I don't know what that is. Okay, unit tests. There are a lot of them, which is good. Let's just randomly take a look at the passes unit test. Doubler plugin. Pass builder bindings test, plugins test. What is the doubler plugin? Is that what this is called? Doubler plugin. I guess this is a test plugin. Doubler module pass. Pass info mixin. Double the value of the initializer. Okay. So we're going to pass in an initializer and double it. And this is just a way to test, I guess, a plugin. Register callbacks, pass, blah, blah. Pipeline parsing callback. If name equals, okay, cool. All right, so here's the main lib directory. I think I already opened some of this stuff, so I'm going to back out of there. Let's see. All right. Selection DAG. Aggressive anti-dep breaker. I like the sound of that. So let's take a look at that. Allocation order. Okay. Assignment track. So these files are at least named super clearly. So when looking at the code, I can tell what they do better than when I was looking at the GCC code. Calc spill weights. CFI fix up. CFI inserter. Critical anti-dep breaker. Early if conversion. Execution domain fix. Fault maps. Inline spiller. LLVM target machine. Live interval loop traversal. Yeah, sure, I'll look at that. Machine branch probability info. Machine check debugify. Machine module, machine loop. So I'm wondering if machine here is the like LLVM machine, the like the virtual, I guess you would call it, machine. So I guess I'll take a look at a couple of these. Machine sync, machine verifier. I'll take a look at the README. Reg is maybe register. Reg alloc fast. Eviction advisor. Save stack. There's a shadow stack. Whoops. Stack frame layout analysis pass. There's a lot of stuff here. I'm just kind of poking at whatever looks interesting. Oh, here's the README. Common register allocations billing problem. Whatever this stuff is can be this, and then merge, mul, and move. So what do we merge? Here's the mul. Okay, how are these different? This one has a move here. This one doesn't. And this also doesn't have a move. But we've gotten rid of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, it also increases the likelihood that the store may become dead. LLVM aggressively lift CSE out of loop. Sometimes this can be negative side effects. This is, I'm not sure that I really understand what's going on here because I don't know what these registers are. Suppose there's high register pressure. R1, R2, and R3 can be spilled. We need to implement proper rematerialization to handle this. Oh, okay. So the loop is going to load this stuff. And I guess this is saying that in some cases, other instructions may monkey with the registers. And is that what rematerialize means? That they need to be like put back where they were? Yeah, maybe. Okay, so we're like recompute, like down here in loop, we've kind of like recomputed these values. It's not always a good idea to choose rematerialization over spilling. If all the load store instructions would be folded, then spilling is cheaper because it won't require new live intervals. Okay. I think that's something I don't have to worry about if I'm not writing a compiler. With a copying garbage collector, derived pointers must not be retained across collector save points. The collector could move the objects and invalidate the derived pointers. Okay, so if we have a copying garbage collector, I guess that means that we copy the some of the values that we're potentially going to garbage collect. Derived pointers must not be retained across collector save points. So I don't know what a collector save point is, but I guess it's a place where the collector can do things more freely, and across some boundary, it can't make as strong guarantees. The collector could move the objects and invalidate the derived pointer. So if you move stuff too much, you can invalidate derived pointers. This is bad enough in the first place, but save points can crop up unpredictably. Consider whatever this is, arrays, load, get element. If the I64 division is lowered to a lib call, then a save point will or must appear for the call site if the collection occurs. To fix this is to copy address calculations so that dependent pointers are never live across. This is actually pretty nice documentation because this is, I guess this is going to somewhat prevent somebody who is new to the code base from introducing a subtle bug that that has incorrect behavior, even though it seems like it would be a reasonable thing to do. Okay, the OCaml frame table structure supports liveness information. It would be good to support it. Okay. The scheduler should also be able to sort nearby instructions by their address. For example, in an expanded memset sequence, it's not uncommon to see code like this, whatever that is. Each of the stores is independent, and the scheduler is currently making an arbitrary decision about the order. So it should be ordered instead, I think is what it's saying. All right. Fun times. All right, selection DAG. Okay. There's a bunch of stuff here. I'm not going to look at all of it. Legalized DAG. I have to look at legalized DAG and legalized types. But I also want to look at target lowering. All right, this re-implements the target lowering class. Is position independent? The target machine, what does it mean to lower a target though? So is it in tail call position? Checks whether a given call is in tail position within its function. If so, it sets chain to the input chain of the tail call. Conservatively require that the attributes of the attributes of the call to match. I'm not sure. Set call lowering info. Attribute flags based on a call instruction and called function attributes. So I don't know what lowering is, but I can at least take a look at maybe what's going on here. So we're collecting a bunch of, I guess, booleans. Call parameter has attribute, and these are all being saved as variables. Is Swift async? Is Swift self? Okay. And what are we doing with all this information? So let's take is in alloca. Is this ever called again? Is there only one match? 1 of 3. Okay. We can set the attributes. If is an alloca, indirect type, call get param in alloca type. So is this doing just some kind of dispatch based on these booleans? I don't know. Maybe. But the code is definitely very readable. Or at least, yeah. For something that's complicated, especially. Keeps track of the state. What am I looking at? Legalized DAG. Okay, let's find out what it means to legalize a DAG. So we've got floating sign as int. This keeps track of the state when getting the sign of the floating value as an integer. This takes an arbitrary selection DAG as input and hacks on it until the target machine can handle it. Okay. So, let's see. So this is actually kind of interesting. Well, I think so. What is a selection DAG? I don't know. So this involves eliminating value sizes that the machine cannot handle, promoting small sizes to large sizes, or splitting up large values into small values, as well as eliminating operations the machine cannot handle. So if we have a target machine, so we have some directed acyclic graph, some which that I'm going to assume for now is a representation of the program in the intermediate representation, and we have to make sure that it's not doing anything that the target machine, which I'm guessing is maybe the architecture, like i86 or ARM or Spark or whatever, that we can generate assembly with that's legal. And so I guess that's why this is called legalized DAG. This code also does a small amount of optimization and recognition of idioms as part of the processing. For example, if a target does not support setcc instruction efficiently, but does support brcc instruction, this will attempt to merge setcc and brc instructions to brccs. Okay. So this is a class. We've got a selection DAG. We've got the target machine target lowering. We've got a set of nodes which have already been legalized. These are the legalized nodes. We hold a reference to it in order to update as necessary on node deletion. And we have a set of all nodes updated during legalization. Okay. And we've got the function. No, this is what? This is a constructor. Selection DAG legalize. You have legalize op, legalize store ops, return a vector shuffle operation which performs the same shuffle in terms of order and result bytes, but on a type whose vector element type is narrower than the original shuffle type. Oh, okay. This must be what the shuffler is up to. So if we're shuffling around bit vectors of length 16, then, and that's not supported by the target architecture, then I guess what it's trying to do is give you the same shuffly goodness, but with a smaller or larger type, which will involve a lot of really fiddly bookkeeping around making sure that you're doing things correctly. That is my guess. Okay, shuffle with narrower element type. Expand libcall, expand fp libcall. Modify sign as int. Replace node. Shuffle with narrower element type. Okay, so let's at least take a quick look at this. Okay, so we've got some get vector num. We're getting the number of elements. Assert num elements growth and cannot promote vector type with fewer elements. Okay, so if all right. So what is it doing here? We've got some stuff with masks, new mask, push back, return DAG, get vector shuffle. Okay. Expand constant FP. Perform insert vector element in memory. Some targets cannot handle a variable insertion index for the insert vector element instruction. In this case, it is necessary to spill the vector being inserted into memory, perform the insert there, and then read the result back. All right. Okay. Legalize load ops. All right, cool. Legalize types. So I guess this is doing the same thing as the other one, except for types. All right. Okay. So, LLVM library visibility, DAG type legalizer, takes an arbitrary selection DAG as input and hacks on it. Wait, what? Legalize types until, wasn't I was looking at legalized DAG, right? So what is this doing with types? Okay, until only value types and it's going to hack on it until only value types the target machine can handle are left. This involves promoting small sizes. Okay, seems like a subset of legalized DAG. Aggressive anti-dep breaker. This implements a register anti-dependence breaking during post-RA scheduling. It attempts to break all anti-dependencies within a block. So what's an anti-dependency? Is that I guess it means a condition that can't happen, that can't hold. Let me see if this is a thing that I can look up. An anti-dependency is an example of a named dependency. That is, renaming variables could remove the dependency. The next. A situation in which a program statement refers to the data of a preceding statement. In a compiler theory, the technique is used to discover data dependencies among statements. Okay, so we just, I guess, walk through the statements and see which variables it refers to, and that creates some sort of tree or graph. So 3 cases exist. Anti-dependency if, what is I? I is a set of memory locations read by SI. If the set of memory locations read by statement 1 and the set of output locations written by S2 is non-empty, then S1 arrow S2 and S1 reads something before S2 overwrites it. Why is this anti-dependence? So S1 reads something before S2 overwrites it. Oh, wait. Maybe this is another condition. This is not like then S1 implies S2. Maybe S1 depends on S2? Oh, okay. An anti-dependency, also known as write after read, occurs when an instruction requires a value that is later updated. In the following, it requires a value that is later updated. Is that good? Is that not good? In the following instruction 2 anti-dependencies on instruction 3, the ordering of these instructions cannot be changed, nor can they be executed in parallel, possibly changing the instruction ordering, as this would affect the final value of A. So we're going to set B to 3. We're going to set A to be B plus 1, and B is equal to, set B equal to 7, I guess. Is that what it means? I don't know. Mul R3, R1, R2, add R2, R5, R6. It's clear that there's an anti-dependency between these instructions. At first, we read R2, then in second instruction, we are writing a new value to it. All right. So we're going to aggressively break anti-dependencies. So we've got a disjoint union data structure to form register groups. A node is represented by an index into the vector. A node can point to itself to indicate that it is the parent of a group, or point to another node to indicate that it is a member of the same group as that node. Okay, so this is a standard disjoint union data set. For each register, the index of the group node currently representing that group that the register belongs to, register 0 is always represented to the group. And we're going to map registers to all the references within a live range. Okay, so we've got this union, this disjoint union data structure, and it's going to, I guess, sort names or nodes into disjoint classes. What is union groups? Register 1 and register 2 groups to form a new group, and we can leave the group. Okay. So I'm looking at the header file, right? So let's see what the actual implementation does. Aggressive anti-dep state. Kill indices. Initialize the vector to indicate that no registers are live. First, everything starts in its own group. I guess this is the initializer, right? So you can get group union groups is live. So we're going to collect the bits out of all registers that are only broken if they are on the critical path for, how did it know where the critical path RCs are? I guess you do stuff and add stuff to the critical path. Bit vector, CP set, allowable set, blah, blah, blah. If critical path set none, do this. Okay. Start block, finish block, observe. Let's see, get path through regs, pre-scan instruction. If reg is current live, then mark that it can't be renamed as we don't know the extent of its live range anymore. Not that it has been scheduled. Now that it has been scheduled. If it is not live, but was defined in the previous schedule region, then set its def index to the most conservative location that is the beginning of the previous schedule region. Okay. As implicit def use, get path through regs. Handle last use. There's a lot going on in handle last use. Pre-scan instruction. I'm going to zoom out here just to see kind of the shape of what's going on. Here's the break. I think this is the break anti-dependencies function. Identify anti-dependencies within the schedule DAG and break them by renaming registers. Okay. So doing some setup. Track progress along the critical path through the S-unit graph as we walk the instructions. This is needed for reg classes that only break critical path anti-dependencies. So, all right, fine. Then we have a bit vector of reg aliases, which I guess is register alias. Attempt to break anti-dependence edges. Walk through the instructions from bottom to top, tackling information about liveness as we go. We've keeping a I think I've gotten disconnected.